señor.
Perdón. I wrote correct. Copy. I think that now I got corrupted. Okay, so for the study, that is defined by this I denoted by alpha. And solutions and consider conditions. One of the things that alpha yeah, for the moment, all of it. Say, varieties. You think that the behavior is subject to the monitoring around that time, the proposition. So we can use the theoretical point of the solution and so let's say you get here. Each of any around 0, equals 0, 1, and 2. So this is branching behavior, how it changes. Because if it changes, it's called modeling. So the modeling, first, our aim is to get this modeling representation. Our aim will 1, 0. These going, that can be read off by easy itself because it doesn't present and ignore this on a good piece of paper. satisfies that structure. They say minus last time routine. So what that is the beginning minus okay. Okay, example 1, we calculate time, x1 was 0, 1, so there, k minus 1, and the last one is plus beta alpha. There is summation. So there is only one close one dimensional number movement. For the one. And then one is reflection. So this result when there is so this is up to the choices. You can see that the solution is near that 1 minus beta A and this means that minus that A this is locally, this is so, here we can here like this, but I have more precise in terms of hypergeometric theories that introduce vectors. So what I mean is that also and if this one is equivalence, one and one the shift from then beta and else the shift over one that corresponds to this. So, in fact, this kind of measurement also it's cumbersome. It's not so. So the important thing, you can remove that also beta K, so K is the K element is one like the other is zero and that is the same. Now, so what happens if I use that condition? So also beta resonance condition. Remove say beta dynamic can be some dynamic constant. Then a solution we should consider. So I have say beta 1 A and get a little bit of it. What we should do is to start from this general. So, in this case, data L different. Data 1 and data 2 are different. And then you have to resonance situation data 1 and data 2 are the same. But we have in complexity those two. One-dimensional solution. So something we must happen. There is really what you shall do is kind of a look show. So, see, there's two. So, that we can do. So what happens if you relative with respect to one? First you get, so first, vector factor is e to the power z times how that will become power minus what is it? Y times log z. Very easy. Then A with one will z one times minus log z. One times, yes. Times is this thing. Plus, this will go on beta 1 times beta 1 of this element. So here, the exponent remains e to the power 1 beta 1. When you want to factor 4 times common, so I have 1 times log z. So this is the case where beta 1 is other definition. So two details function. If you have given more. And the relationship. Okay, so this one is everything is multiplied by rounding about difference 1. And add the A runs from 1 to n. So, let's say the monotony condition, the monotony on 0 will be calculated Jordan block size plus n. Okay, so the open monotony is 0 of this form is into the power of 1 to color. So this is now, so our aim is to get this more represented. So, before doing this, to consider a bit on the about determinism and algorithmism numerisms I've mentioned. But how about other detailed numerisms? Can we yes, in certain sense we can, but we think the price is higher and also beta other numerisms. So, how about removal? In fact, it is not about the common reason. The question is where the monotony notation instead of go on, I write it and this homomorphism. From the function of the group, we want to point to GKZ. And also one another representation reason that there exists there are such that online always Such that there is invariant under the action of the rules of Euclid. Such a system otherwise modern invariant. Invariant subspace subspace. So first question is this. Of course it is rather pleasant to get this way. And in fact, I can give you absolute only in the case where this location is very subtle. Fight. Case. For some district of a 1% net. Okay. And this turned out to be and these matters that get only so what is the operator so our hyper operator want to consider this kind of shift. So for this purpose, this is the GKZ box of variance 1 others are same. Left and left equals so it's let me say, alpha j plus 1. J
yeah, this condition. Yeah, this condition. Yeah. Say, assume that you have beta j equals some beta j equals beta I minus 1, say. Assume, say, alpha k equals beta k minus 1. Huh? What happens? That is, say, then the operator factor out k minus 1, isn't it? Minus j equals 1 to k minus 1 of theta z plus beta j minus 1. Yeah. Times theta z plus alpha k. So theta z plus beta k minus 1, yeah, it is the same operator at the end. So it factors from right. That is, say, this kernel, in this case, contains very simple one-dimensional kernel, one-dimensional vector vector space spanned by the solution of this differential equation. That is, say, it is c times z to the power minus alpha k. One-dimensional vector space you have, and this space. So this space. Take this space. Let me know about the V prime. V prime is invariant. Is monotone invariant. So it's evident, isn't it? So that if H0 around 0, it acts like e to the power minus alpha k. At infinity, it acts as plus, and at 1 it is aridity, isn't it? So there is no singularity. It doesn't branch at z equals 1. So it is identity. So that's it. We find a one-dimensional vector subspace if the situation is like this. But so making use of these this procedure, maybe I shall write down commutative diagram. Commutative diagram. So I have V alpha minus 1 ej. So only the j's. That is alpha j minus 1 instead of alpha j. Then after the action of it will change into V alpha beta. And after monodromy action, so monodromy this one, LP. LP is one of 0 infinity. It is analytic continuation. Of course, it doesn't change. It is k-dimensional vector space, so it doesn't change. And of course, here also I have So in this manner, we can continue as much as you want. Alpha, you can shift alpha by an integer, anyone, till the moment when, or plus also, of course. Plus direction also possible. Till the moment when this situation arrives. If this situation arrives, then the monodromy representation is reducible, and it has dimension one-dimensional invariant monodromy invariant subspace. It's in one word. It's k-dimensional. It's one dimensional. Okay. So this is a kind of that is say. So V prime. Till the moment when it's so this way or this way, as for beta also, till the moment when it is decomposed into V alpha plus M beta plus L something that is quotient by V prime. Some direct sum, till the moment when you get direct sum. But V prime, as V prime, we shall take these, the space, so where the V prime is, so C of Z to the power minus alpha L, where L, so else, such that alpha L minus beta J Z for some J. So A runs all alpha A runs all over these parameters. That is, say, yes, you can have theta zeta plus alpha k minus da 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 da. Something times with this, then it can be factored out, and again you can repeat the same procedure. Such that remaining beta j, there may be something that coincides with alpha up to integer shift, and you remove all these, or you factor out all these operators, and you get this invariant, monotone invariant, non-trivial invariant space. That shows you that it is reducible. Yeah. Okay. So it is. In fact, I need to explain more. This is. I follow the wonderful article by Dutch. Two of our colleagues, Fritz Lucas and Ger Ekman. No, these are Dutch, Netherlands. These are from Utrecht. They're both of them also in Leiden. At that moment, so he retired from Utrecht University, and he retired from Nijmegen. Invenciones Mathematica, 1989, I think. I have it. Yes, 1989. Monodromy for the hypergeometric function and fn minus 1. Yes, it's true that it is very ambitious title, but it deserves. Yes, this article covered gave answer almost all important questions on the monodromy. Especially completely decided the parameters alpha beta when the monodromy group is finite. That is, say, when this Pochhammer hypergeometric function be algebraic function. Yeah. So for finiteness. I don't know whether I can formulate next week, and maybe I can try to formulate the result of the main result of this, one of main results, yeah, of this article. So it is Drinfeld. Usually this so Spring article is not accessible, not free access, but Vladimir Drinfeld put it on his site and and his site in homepage in Chicago, and so when I quickly need to look at this paper, I go to his site in Chicago. Yeah. So this is really very important. And so for the case of Bohoma hypergeometrics. Yeah. Now, so the important thing is that this operator, so like this case, the typical this case, admits factorization, factor out. So this part, yeah, for this part, has order k minus 1, and this first order operator. In this case, that dimension 1 vector subspace and dimension k minus 1. This kind of splitting happens. Splitting happens, yes. That is, say this is reduced. So, in short, the splitting happens if alpha I and beta j, the difference of alpha and alpha j is an integer. The splitting happens if and only if alpha I minus beta j an integer for some there exists some pair, yeah. So this is removal, absence, resonant alpha beta resonant condition, resonance. And if never happens, then alpha beta non-resonant condition. Non-resonance. Alpha beta non-resonance means that alpha I minus beta j never coincides for all ij. So, and this means that it is equivalent to say that monodromy representation, yeah, is irreducible. Okay. So such kind of splitting doesn't happen in the case when these are all different. Yeah. Okay. So let us assume from now on this to get this monodromy representation. Let us assume restrict ourselves to the case of irreducible monodromy representation. So, there are several And in fact, so now I reformulate so our aim is consider this, but instead of considering these matrices, let us look at characteristic polynomials of the monodromies. Monodromy matrices. So the proposition that so this z equals 0 has 1 minus beta s, isn't it? Characteristic exponents. Z equals infinity hat alpha s. Yeah? That means that determinant of identity k minus or t minus t times inverse would be will be k t minus e to the power beta e to the power 1 minus beta s equals product beta s. In fact, beta n minus 1, but I can. So, under beta, so of course, beta and alpha beta, non-resonance. No, everything, yes, non-resonant. Whether I need it. In fact, I don't need it, yes. Non-resonant. Yeah, that we saw it that H0 has something like this. Minus beta 1. And you remove them and multiplies more than m times. Then so they vanish, yeah? So yes, this will give us zero matrix. So yeah, in fact, there is no need to consider alpha beta non-resonant, alpha or beta non-resonant. Yeah, only alpha beta non-resonance. No, to the moment we don't talk about non-resonance. Simply look at these characteristic polynomials. Polynomials of say H0 inverse, and H infinity. That must give us e to the power 2 pi alpha L L yeah, that's it. So, in fact, in the irreducible condition means that these two polynomials have no common factor. That is, if the difference between alphas and betas are always non-integer, never be integer. They can have common factor if and only if they common factor means it is the same condition, equivalent condition. common factor that it is excluded. So these factors, these polynomials, have no common factor. Vertex polynomials. Now, so the answer to this question I formulate in terms of these polynomials. So it is degree k polynomial, both of them. It is t to the power k plus a1 a to a k. I think it's a1 tk minus 1, yes. And this one is t to the power k plus b1 t to the power k minus 1. So there exists a's in general. These are complex numbers. But we are interested in, so in the case when these are integers, alpha i's, very special situation. That happens in algebraic geometry. The monodromy of so let us define. So alpha, a, I, and a, k are defined by this manner. So these are symmetric polynomials of these numbers. Units, complex numbers located on a unit circle. So we get two vectors in CK. And from this, we construct two matrices, let us denote by A matrix by this one. So first, this is so 0 and so no, sorry. It is k minus 1. Yeah. So this is k minus 1 times k minus 1 unit matrix, and here I have a minus k etc. minus a1. I put this kind of define, so define. The following two matrices. And the second one is the same situation. Identity of k minus 1 here. And the last column will be given by this. In fact, you see immediately that the characteristic polynomial equals to this. equals to this. And in a similar manner, characteristic polynomial of B simply, so maybe I can do it in a very simple case. Where is 1? The simplest case is, I think, this one. So t plus a1, a2, minus 1, let us take the determinant, equals t squared plus a1t plus a2, isn't it? It's written here, k equals 2 case. So for general case also, the proof is very easy, and you see that it really the characteristic polynomial of this newly defined two matrices give the same polynomials. But the analogy doesn't stop here. The statement is that, in fact, there exists a basis. So theorem means tells that there exists a basis of V alpha beta such that this so there's a special choice of basis of this k-dimensional C-vector space such that it gives you concrete representation in terms of these. So, in general, this characteristic polynomial is very weak. So it is information so far less than this matrix representation, but it turns out in the case of hypergeometric function for homo-hypergeometric differential equation, the monodromy hypergeometric differential equation, the data, the information of characteristic polynomials are enough to recover the global monodromy. The global monodromy can be recovered from here, from so that is a L0, L infinity, isn't it? So this is so L0 is induced by analytic continuation of solutions induced by the movement along a loop of this loop are called H0 and H infinity. So, and third one also, and you see immediately that the H1 it is KK. So H1 is this, in fact, thanks to this relation between the triviality of these composition of three groups. From this you can get the monodromy around H1 and around Z plus 1. But this one is as you see that here, very similar. So there, this one is also identity k minus 1. And it is a very, very easy calculation to see that this one has rank 1. So this matrix H1 minus it is even A minus 1, A minus B, isn't it? Yeah, A minus B. But what is A minus B? A minus B is 0. It is completely 0. And last term, so last column has bk minus ak and so on. That is, say, it has rank 1. H1 has rank 1. Rank of H1 minus identity k is 1. That is, say, and H1 is pseudo reflection. So pseudo reflection, that is, say, so 1, 1, 1, something. In fact, it is exactly the matrix that I wrote, and in deciphering this z equals 1 characteristic exponent, characteristic exponents z equals 1 was 0, 1, k minus 2, and gamma. Beta minus alpha. That is it, yes. So, in fact, so this one is, yeah, pseudo reflection, maybe you studied complex reflection last year. So it comes from here. Of course, it has geometrics and the topology of Picard-Lefschetz type interpretation. Yes, is possible when this differential, these hypergeometric functions can be understood as the pairs of algebraic varieties. So this part is also Torah, yeah. Okay, so last lecture, I will explain the theorem, the proof of the theorem, and maybe I try to explain the main result of Bukas-Heckman on the algebraic. Maybe better to explain rather this result on the application to number theory, arithmetics, than to explain mirror symmetry, because mirror symmetry persons were absent, or I don't know whether they, in any case, those who wanted to follow this lecture to get knowledge on the introductive to mirror symmetry did not appear, so I think that it's better to explain the application to arithmetics. Yeah. Okay. So